All right, welcome back, and we'll go through some examples of using partial fraction decomposition to integrate functions. We learned that it's possible to take a rational function, which is a polynomial on top divided by a polynomial on the bottom. We learned we could take that if the denominator of the bottom polynomial can be factored. Then we can rewrite a rational expression as a sum of two simpler rational expressions. We're going to use that in order to integrate this function. Step 1. Decompose (48 minus 4x) over x squared minus 4x minus 12 equals, well, we had to factor it first before we know what form the decomposition is going to take. So it's 2 brackets, x times x gives me my x squared. Now I want the mystery numbers, so using a product and sum method to factor. Mystery numbers are multiplied to give negative 12 and add to give negative 4. So negative 6 and positive 2. Multiplied to give negative 12, add to give negative 4. So our theorem states that this can be reduced or rewritten or decomposed as an unknown constant over the first term in the denominator. So a over x plus 6 plus b over x plus 6. And actually, I'll jump back to something mentioned in the last video. I forgot to highlight this part here. The degree of the top polynomial must be lower than the degree of the bottom polynomial for us to be able to guarantee that this type of decomposition can be done without any intermediate steps. So that is important. And it's not important in the example we're working on right now, but it'll be important in a future example. Anyway, back to the problem. So if this is the form of the decomposition that we're going to do without the typo, plus 2, not plus 6, then we're going to have to find a and b. We're going to have to find the unknown coefficients. I'll use the special method where we get rid of the denominator, multiply both sides by x minus 6, multiply both sides by x plus 2, and cancel everything that cancels. And we get 48 minus 4x is equal to a times x plus 2 plus b times x minus 6. This is true for all x. We have to be smart though. If we want to find a and b easily without making a system of equations, we have to choose x values that will make one part of this expression disappear. So I can make the first part of the expression disappear if I let x equal negative 2. So let x equal negative 2. I have to replace all the x's with negative 2. So 48 minus 4 times negative 2 is equal to a times negative 2 plus 2 plus b times negative 2 minus 6. So I'll have 56 is equal to 0 minus 8 times b so that means b is equal to negative 7. 56 divided by negative 8. Now how do I find the second value? How do I find a? Well, I want the second term, the right hand side, to disappear, b times x minus 6. To make that term disappear, I'm going to let x equal 6. So now we have 48 minus 4 times 6 is equal to a times 6 plus 2 plus b times 6 minus 6. So 48 minus 24 is equal to 8a plus 0 So 24 is equal to 8a. We can divide both sides by 8, and we get a is equal to 3. So this decomposition tells us, or this stuff we just did, it tells us, thus, 48 minus 4x over x to the squared minus 4x minus 12, that's equal to a over x minus 6, so 3 over x minus 6 plus b over x plus 2, so minus 7 over x plus 2. That was step 1. Now we do step 2. Now we integrate. Integrate. So integral of 48 minus 4x over x squared minus 4x minus 12. We can rewrite that as the integral of 3 over x minus 6 minus the integral of 7 over x plus 2. For the first integral, we use substitution. We would let w equal x minus 6. For the second integral, we use substitution. We'll let w, or I guess u if you want. Well, we're already using u for something else, but I'll just use a different color. W is equal to x plus 2. Different color w, a green w instead of a yellow w. And when we do this substitution, what we'll get is we'll get 3 ln absolute value of x minus 6 minus 7 ln absolute value of x plus 2 plus c. That'll be our answer. So to take a step back, we first decomposed the rational expression into 2 simpler rational expressions. We followed that by integrating each of those expressions. Each integral required us to use a substitution. I didn't show the substitutions. You can work through them on your own. dw is equal to dx in each case. So it works out very neatly. They're both integrals of the form 1 over w. Antiderivative 1 over w is ln absolute value of w. Undo the substitution, and there you have it. The hardest part of a problem like this is the step at the beginning where you identify that partial fraction decomposition is how to do it. It's identifying the correct strategy to use. Here's another one. We want to find the integral from -4 to -3 of this function, 2 over x squared minus 4 integrated with respect to x. And you know, if this wasn't in a section that was called partial fractions, you might try substitution. You might try, I'm going to let w equal x squared minus 4, or I'm going to let w equal x squared, and see where that leads. And it doesn't lead somewhere very nice. So I'm going to do what we did in the last example, step 1. I'm going to decompose 2 over x squared minus 4 equals 2 over, I got to factor this. This is a difference of squares. It's x minus 2 times x plus 2. So that means this will factor into a over x plus 2. Or I'll put them in the same order I have them written there. A over x minus 2. Not that it matters. I'll just be consistent. Plus b over x plus 2. We need to find a and b. So I'm going to do the cross multiply thing. I get 2 is equal to a times x plus 2 plus b times x minus 2. This is true for all x. True for all x. We can choose any x value we want. It has to be true for that x value. I'm going to choose an x value that's smart, like, let's say -2, because that'll make the first piece disappear. So I make that choice. 2 is equal to a times -2 plus 2 plus b times -2 minus 2. So 2 is equal to 0 minus 4b. And then that means if I divide both sides by -4, we get b is equal to -1/2. Now we need another one. We need the a value. So I'm going to choose x is +2 this time. So replace all the x's with 2's. We have 2 is equal to a times 2 plus 2 plus b times 2 minus 2. So 2 is equal to 4a plus 0. We divide both sides by +4, and we get a is equal to 1/2. So we can conclude that 2 over x squared minus 4 is equal to a over x minus 2, so 1/2 divided by x minus 2 minus 1/2 divided by x plus 2. Making sure we put the right coefficient over top of the right part according to how we labeled it up above. Yeah, it looks weird if the 1/2's that way, but it's fine. It's just a number. You can put 0.5 if it bothers you. Now step 2. We're going to find the antiderivative. So the integral of 2 over x squared minus 4 dx by throwing in their decomposition. So this is the integral of 1 over 2 divided by x minus 2 minus integral 1 over 2 over x plus 2. For this first integral, well, I'm going to do another step. I'm going to take the 1/2 and put it out front. Integral 1 over x minus 2 minus 1/2 integral of 1 over x plus 2. And each of these requires substitution. So this one, we'll use w is equal to x minus 2. And for the second one, we'll use w is equal to x plus 2. dw is equal to dx in both cases. So it works out very neatly. We have 1 over w antiderivatives again. So 1/2 ln absolute value of x minus 2 minus 1/2 ln absolute value of x plus 2 plus c. So that's that one. But we need step 3. We have a definite integral. We have an integral with bounds. So the integral of 2 over x squared minus 4 dx from minus 4 to minus 3, that's going to be capital F at -3 minus capital F at -4. Just evaluating our antiderivative at the top bound and bottom bound and subtracting. So 1/2 ln -3 minus 2 absolute value, so ln 5, minus 1/2 ln 1. So that's the f of 3 part, minus the f of 4 part, 1/2, or f of -4, ln of -6, absolute value, so positive 6, minus 1/2, plug in, so -4 plus 2, -2, absolute value positive 2. Ln of 1 is 0. And we end up with 1/2 ln 5 minus 1/2 ln 6. And then we have a double negative, 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 so plus 1/2 ln 2. And that'll be our answer. Yeah, you can factor the 1/2 out. You have 1/2 ln 5 minus ln 6 plus ln 2. And then you can use fancy log rules to simplify it as 1/2 times the ln of 10 over 6. So ln of 5 over 3. And then you can bring the 1/2 up as a square root. And you have ln of the square root of 5 over 3 as your answer. But don't do that. Leave it like this. It's hard enough. Don't make it harder. Now, what we've had so far are rational expressions where the top polynomial has a lower degree than the bottom polynomial. What happens if that requirement isn't met? So P of x over Q of x, rational function, with P of x degree not lower than Q of x degree. It turns out that in this type of a situation, we can't immediately go to a partial fraction decomposition. What we need to do is we need to use a trick. Here's the trick. I mentioned that multiplying, like way earlier in the course, mentioned that multiplication by 1 is powerful. It's like this secret method in mathematics for solving problems. Multiply by 1. Just use the right form of 1. You can solve any problem. Except for problems like this. There isn't really a right form of 1 that you could use, although maybe there is. Let's not look for it. I'm going to use an alternative, super powerful mathematics strategy. Watch this. Watch this. You're going to love it. I'm going to do something so amazing. Bam. Oh yeah, I added 0. But how? Like, how does this help anyone? How does adding nothing, like putting a plus 0 in the expression, how does this accomplish anything? And the answer is, well, you have to use the right form of 0. The right form of 0. Isn't there only one? No. There's many things that are 0. For example, so I'm going to pick something that isn't particularly helpful, and it's even worth color coding it. I'm going to put plus 10, and to make sure it's adding 0, I have to do a minus 10. Like, I added nothing. I added 10 and I took it away, so no change was made. But this isn't helpful. Like, I can't do anything with this. But what I can do something with, I added 10 and then I took 10 away. I could also subtract 10 first and then add it. I could do that, right? That's also another way to add 0. But that's not helpful either. What I'm going to do is I'm going to subtract 4. I'm going to add 4. I'm choosing 4 because look what's in the bottom. Now what? Why is that nice? Because I can use a fraction rule. I can write this as x squared minus 4 over x squared minus 4 plus 4 over x squared minus 4. I maintain the color coding. And look at that first fraction. X squared minus 4 over x squared minus 4. That's just 1. So there's a 1 there. And now we can decompose that second term. Partial fraction decomposition of 4 over x squared minus 4 equals 4 over x minus 2 times x plus 2 is equal to a over x minus 2 plus b over x plus 2. Now it's possible, because the degree of the top polynomial is a degree 0, the degree of the bottom polynomial is degree 2, so the top has a lower degree than the bottom, and we're guaranteed an ability to use a partial fraction decomposition whenever the denominator factors, as long as that first condition is met, that the top polynomial is a lower degree than the bottom. All right, so now we have that task to do. So I'm going to do the common denominator thing. We have 4 is equal to a times x plus 2 plus b times x minus 2. I'm going to make a choice. I'm going to choose x is equal to negative 2 first. So we get 4 is equal to 0 minus 4b. And it tells us that b is equal to negative 1. And I'm going to choose x is equal to 2. When I do that, I get 4 is equal to 4a plus 0. And it tells me that a is equal to positive 1. Okay, so then we can rewrite this as 1 plus a over x minus 2, so 1 over x minus 2 minus 1 over x plus 2. So that was step 1, decompose. Now we can integrate. So we have the original integral, x squared over x squared minus 4. We can rewrite that as this integral of 1 plus the integral of 1 over x minus 2 minus the integral of 1 over x plus 2. For the second integral, we'll use w is equal to x minus 2. For the third integral, we'll use w is equal to x plus 2. And for the first integral, we don't need a substitution. The antiderivative of 1 is just x. So we get x plus integral of 1 over w dw. So ln absolute value of w, undo the substitution. So ln absolute value of x minus 2. Minus, do the same thing here, we get ln absolute value of x plus 2. And a big plus c. That's it. I really shouldn't say that's it, because it's not very easy. In particular, if you don't know that you're supposed to do certain steps, that you have to reduce the quadratic. You have to reduce that top power to make it lower, so that we're capable of using this type of a decomposition. And once we figure out the strategy, it's fairly mechanical, but it is hard. Okay, here's something else that can happen. We could have an integral where it doesn't look like a polynomial at all. Integral of 12 sine of x over cos squared, or cos x all squared minus 9. And I purposefully put the cos of x inside the all squared instead of writing it as cos squared of x. And there's different approaches you might take when you see this problem. You might say, I'll let w equal cos of x I'll let w equal cos of x all squared. I'll let w equal cos of x all squared minus 9. And I mean, I'm not even sure which strategies will work other than the one that I'm certain will work. Like, there's probably several methods that can be used to integrate this. But I'm going to show you a neat trick. I'm going to start with substitution. Start with substitution using w is equal to cosine of x. So I have an integral of 12 times the sine of x, that part doesn't go away yet, over w squared minus 9, and I got to replace w, or the dx, with something in terms of w. So dw by dx is negative sine of x. Rearrange, dx is equal to negative dw over sine of x. So that's good. You can tell now that that's a good substitution, because look what happens. Sine of x on top cancels with the sine of x on the bottom. I'll put the negative sign out front. So negative, I'll put the 12 out front with it. Well, maybe I'll leave the 12. Maybe I'll leave the negative and I'll leave the 12. Negative 12 over, you can bring it out if you want, w squared minus 9 dw. And now I'm going to use partial fractions decomposition. We're going to decompose negative 12 over w squared minus 9, which can be rewritten as, I'm going to factor the bottom into w minus 3 times w plus 3. And then that's going to be written as an unknown constant a over w minus 3 plus an unknown constant b over w plus 3. Now we have to find a and b. So I'll do the common denominator thing, multiply both sides by w minus 3, multiply both sides by w plus 3, cancel, and we get negative 12 is equal to a times w plus 3 plus b times w minus 3. This must be true for all x, or it must be true for all w, or all w. So I'm going to choose w is equal to negative 3 to start things off. So we have negative 12 is equal to 0 minus 6w. So that tells us that w is equal to 2. Divide both sides by negative 6. We can go back and then choose a different w value. We'll choose w is equal to plus 3, and that will make the second term disappear. So negative 12 is equal to 6a plus 0. That means that a is equal to or w is equal to negative, not w, 6. I'm sorry. My apologies. I'm not solving for w. It's 6, what am I solving for? If w is equal to negative 3, it's 6b. So b is equal to 2. Okay, and then for the second one, I have a is equal to negative 2. There. Sorry about that. Okay, so I'm going to take this and I'm going to use that to rewrite the integral. So we have the integral of a, negative 2, over w minus 3 dw plus the integral of 2 over w plus 3 dw. And we can use substitution again. I hesitate to use the letter w, so I will use a different letter. So let's say let y equal w minus 3 for this one. And for the next one, let y equal w plus 3. Do the substitution, and we get negative 2 ln absolute value of w minus 3 plus 2 ln absolute value of w plus 3 plus c, and we're not done yet. Our original integral was in terms of x. We have to undo our big substitution. We have to go and replace all the w's with cosine of x. So negative 2 times ln absolute value cos of x minus 3 plus 2 ln absolute value cos of x plus 3 plus c. Think about all the different things that have been incorporated into this question. Derivatives of trig functions. That was necessary to do the initial substitution. Partial fractions decomposition. Within that, once we got to a decomposed rational expression, we had to use substitution again inside each of those pieces. And then we had to undo the substitution. So lots of stuff contained inside one problem. Very dense in terms of how much course material is embedded into here. Here's a better question. Now these questions can be extremely time consuming. So here's a format that tests some of the same content, less time consuming. We're told that ax plus b over cx squared plus dx plus c is equal to 12 over 4x minus 3 minus 15 over 5x minus 1 for some unknown constants a to e. And then we're asked to determine what is the integral of 3ax plus 3b over cx squared plus dx plus e. So what I want to be able to do is I want to relate the question to the information that's given to us. I can factor a 3 out, and look what happens when we do that. 3 times ax plus b over cx squared plus dx plus e. And then I can bring the 3 out front. 3 times the integral of ax plus b over cx squared plus dx plus e. And now I'm going to use the fact that that's equal to integral of 12 over 4x minus 3 dx plus 3 integral of the second piece. Or let's put a minus in front since it's being subtracted. 15 over 5x minus 1 dx. So I'm using this statement here, right there. I'm going to simplify each of these. I'm going to take the 12 and put it out front, so we have a 36 integral of 1 over 4x minus 3 minus 45 integral of 1 over 5x minus 1. And then I'm going to do those integrals off to the side. So how do you integrate 1 over 4x minus 3? You have to use substitution. You have to let w equal 4x minus 3. So I'll do this one in whole. I won't skip any steps for this one. So dw by dx is equal to 4, or 4 minus 0, which is 4. And then that means dx is dw divided by 4. So we can rewrite our integral. I'm going to make it easier to read. integral of 1 over 4x minus 3. So w is equal to 4x minus 3. dw by dx is 4. So dx is dw divided by 4. So I'm going to rewrite the integral as the integral of 1 over w. And then replace the dx with dw over 4. Which is 1 over 4 integral of 1 over w. Antiderivative of 1 over w is ln absolute value of w plus c. And I'm going to undo the substitution, so 1 over 4 times ln absolute value of 4x minus 3 plus c. So that's the first piece. Over 4 ln absolute value of 4x minus 3. So 9 ln absolute value of 4x minus 3. And the second part, we have another integral. So integral of 1 over 5x minus 1. So I'm going to let w equal 5x minus 1. dw by dx is 5. So dx is dw divided by 5. And then that allows us to rewrite the integral as 1 over w dw over 5. So 1 over 5 antiderivative of 1 over w. 1 over 5 ln absolute value of w. And then plus c, and then undo the substitution. So 1 over 5 ln absolute value of 5x minus 1 plus c. And that'll get plugged in over the left-hand side for the second part. Minus 45 times that thing, 1 over 5, not 1 over 2. How did that happen? Okay, so 1 over 5 ln absolute value 5x minus 1. Now each of these had a plus c, and I'm going to combine both plus c's together into one big purple plus c. And then I should simplify that last term. 45 over 5 is 9. 9 ln absolute value of 5x minus 1 plus c. So we had to identify that the partial fraction decomposition was important. We had to plug it in, but we also needed to factor a 3 out front. That 3 survived and multiplied both components of our decomposition. And those two integrals weren't trivial to do. I'm going to go back to the beginning of the note and add a formula right to the start. That's going to be helpful for all of these partial fractions integrals. So a little note here. Note. Shortcut antiderivative formulas. Important for this section. So the formula that's going to be really important for the section is the antiderivative of 1 over ax plus b is equal to 1 over a times ln absolute value of ax plus b plus a constant integration. But anyway, it's worth reminder, the antiderivative of 1 over f of x is not equal to ln absolute value of f of x in general. So it cuts down your work substantially if you just know the shortcut. So just a really quick application of the formula. I know I'm dragging the video on, it's already at 40 minutes. Antiderivative of 1 over 3x plus 7 dx. This formula says that this is going to be 1 over 3 times ln absolute value of 3x plus 7 plus c. And if we didn't have the formula, we'd have to use substitution, let w equal 3x plus 7. It just comes up so often, like flip back and look at all the examples. Almost every example, I think almost every piece of every example required using this type of integral and could have benefited from the shortcut. Anyways, see you next time.